Hello and welcome. This is the Pre-Calculus Spring Final Exam Review video for chapters 1 through 3. And we will have 80, count 80, example problems here. Functions and their graphs, polynomial and rational functions, complex numbers, and exponential and logarithmic functions will all come into play. Now some problems will require a calculator. So I have my handy dandy TI-83 right here that I'll use for some of those problems. Now, most of the time whenever I do these review things, normally I reteach problems as I go. Because there are 80 problems, I'm going to kind of just go through the steps and kind of talk about them, not show alternative ways and all this stuff. I'll just talk through a problem as I do it. Hopefully it speeds up the time pretty well. Okay, we're going to start with problems 1 through 4 where we will evaluate each function. I have w of x equals 3x plus 4. I have to find w of 4. Now, finding w of 4 means substituting 4 in for x, and the value you get out for y is your answer. This will be 12 plus 4, which is 16. This does mean there's a point on this graph that is 4, 16. Say 4 for x, 16 for y, or w of x. Number 2, g of a equals a plus 5. Find g of negative 9. And again, when I'm stating this stuff right here, this time negative 9 is taking place of a. And let's see, what was I going to say about this? Oh, the thing inside here takes place of that variable no matter where it goes. Inside here could say the word booger, and booger would take place of it. Not that we could evaluate much with booger plus 5. Of course, and anyway, so that answer is negative 4. G of negative 9 is negative 4 as we substitute. Number 3, g of a equals a cubed minus 4a. Find g of negative 4. Once again, substitute. We're going to take negative 4 and cube it. This will be minus 4 times negative 4. Note how I'm using parentheses here. It's quite important that you use them as often as possible for substitution if you can. Negative 4 cubed is negative 64, not positive. Negative 64 plus 16 is negative 48. G of negative 4 is negative 48. And last time I said x and y, this would be a and g of a. I guess I can't always call them x and y. Number 4, g of t equals 2t minus 4. Find g of negative 8. And again, there's not much more to say after this. Just following the work, substituting what's in place of there. Probably nice, good warm-up problems to just get you started. G of negative 8 apparently is negative 20 here when all said and done. So just make sure your calculation's right. All should be good for those first 4 problems. Okay, find the inverse of each function. G of n equals 4 over n plus 2. This is number 5. What I'm going to look to do here is find the inverse function of n. This will, whoops, not of x, of n. And the notation will look like this here. This equals. And what's going to happen is you have 2 variables. And, you know, for the time being, I'm not really good at saying what this other actual variable is supposed to be besides g. But whenever we do this with y and x, what happens is we have y take x's place, and then we solve for y again. That would be the inverse function in itself. So the swap comes right here. The end result is we still want it to have to say a y equals equation. Not that it's truly y anymore. It's the inverse function now. So to solve for y, I'm going to multiply both sides by y plus 2. And look, we're using different variables in the end there. G and n, I'm going to use those in the end as well. Y took place of g, x took place of n. Multiply both sides by y plus 2. This is now gone, and now I have y plus 2 times x equals 4. There's no reason for me to distribute this x into y plus 2 because I got to get y by itself. So let's divide by x next, and we'll get y plus 2 equals 4 over x. Subtract 2, you'll get y equals 4 over x minus 2. Now this is the answer to this question, but in terms of inverse function of, we should put in n instead of x right here, and g to the negative 1 of n instead of y. So it should say 4 over n minus 2. And I'm probably going to do this for most problems. I'm just comfortable with it that way. I'm sure you will be as well, and you can take a look at that result, and that should be good. Yeah, that's all I got there. Number 6, g of x. Well, at least this one's now at x here. So I'm going to have y take place of g of x. And the only reason why I'm having y actually take place here instead isn't just because it's a y, but also because I like this to just be one variable. I wouldn't want this to say f of x either. because I'm going to rework this stuff, I'm going to have y take place of x. I want it to look like a variable. I think that will help me most when I'm attempting to solve these problems. Let's multiply both sides by 2, shall we? Okay, let's get y by itself. I have negative y minus 3 equals 2x. I'm going to add 3 and then divide by negative 1, or, switch signs, y equals negative 2x minus 3, or inverse function of x equals negative 2x minus 3. And this variable this time was still an x. There's our answer. We'll see how long I use this blue color. Every so often I feel like I want to change my colors up. Number 7, g of x equals negative 2 over x minus 2 plus 1. Okay, the one thing to be careful of is this negative sign. It only applies to either the numerator or denominator. I'm going to apply it to the numerator. That'll be easiest for me. If I did apply it to the denominator, understand that would be negative 1 times this amount. So if I had it in the denominator, both signs would have changed, not just one of them. Okay, right here, this is, whoops, I want to make this say y equals. Y equals this. Let's swap x and y to take its inverse. X equals, boom, now we're looking at inverse function. And let's get y by itself again to note it as the inverse function notation. They're not asking us to graph these, by the way, but if we did graph them, I'm going to subtract 1 here. But if we did graph them, the inverse functions would appear the same, like they would look the same, except mirrored across the y equals x line. That would be its axis of symmetry. So if you tilted your head 45 degrees, then you would actually get that result here. So this is y minus 2 times x minus 1 equals negative 2. Again, don't need to distribute here because I need to get y by itself. I'm going to divide both sides by x minus 1. So I have y minus 2 equals negative 2 over x minus 1. Or add 2 to both sides here, we'll get y equals negative 2 over x minus 1 plus 2. You could put the 2 in front as well. I have an answer key right next to me, by the way, that I'm taking a peek at to make sure I have my answer match theirs. Or at least I look at it at the end. Right there, I just noticed, okay, here's the same answer. Plus 2. Boom. There's your final answer there. Remember, that negative 2 can appear in the middle again if you need it to. Finally, number 8, g of x equals 2x cubed, or y equals 2x cubed. Swap x and y. X equals 2y cubed. Solve for y, divide by 2. I'll get y cubed equals x over 2. You might say 1/2 x, but the answer key looks like it has it this way. Take the cube root of both sides, okay? Cube root of both sides. And this will say y equals cube root of x over 2, or inverse function of x equals cube root of x over 2. Now, what's kind of strange about this, and we haven't played with this, I think, at all yet, but normally they ask you to rationalize denominators, and this would be an irrational answer. But this is what the answer key shows. So what I'm going to write over here in green is what we would do if we wanted to rationalize this denominator. Because remember, this truly is cube root of x over cube root of 2. So how do we rationalize this denominator? You might say multiply top and bottom by cube root of 2 over cube root of 2. And you'd be right, but this only gives you the cube root of 4. You have to do it twice. Cube root of 2, etc. So technically here, this whole thing is cube root of 4 times cube root of 2, which is cube root of 8. And the cube root of 8 is 2. On top, you have cube root of 4x. 2 times 2 is 4 times x. Boom, right there. This would be a more appropriate answer to me. What the key shows, of course, is this one right here, though. So I'm going to leave this one be like that. But here's another appropriate response. Probably even more appropriate. Perform the indicated operation. We have g of a equals this and h of a equals that. We have to find g plus h of a, number 9. Okay, for these kinds of problems, it's probably best that you note another way that this can be written. G of h plus a can also be written as g of a plus h of a. I normally transcode it like this first to get myself started, because then I know exactly what's going on here. I'm going to be adding 4a plus 1 with a squared minus 4. There's no reason to have these in parentheses for now, but you can tell if we do subtraction or something. It looks like we don't. But if we did subtraction or something, this minus is really important for this set. Now, a squared combines with nothing. 4a combines with nothing, but 1 combines with negative 4, such that, and I'm going to write it in standard form, 1 minus 4 is negative 3. So g plus h of a equals a squared plus 4a minus 3. That's your final answer there. Number 10, h of x, g of x. Let's find h over g of x. Now, likewise with this right here, you can rewrite this as h of x over g of x. And this becomes 2x plus 1 over 4x minus 5. Now, here comes a teaching moment right here. This is actually your final answer. There's nothing else I can actually do here. You might say, do we have to multiply by conjugate down here? No, we'll do that with complex numbers. Can these cancel? Can we make this x over x, make this 1/2? No, you cannot do that. You can only do that if there's a common multiple or factor on top and bottom. What I'd look for here and see if there's a common factor on top and bottom, there's not. If this was 4x plus 2, yeah, there'd be a common factor of 2x plus 1 on top and bottom. I could cancel. That's not the case here. This is all you're left with. Leave it like that. Number 11, h of n equals 3n squared minus 3, g of n equals n minus 3. Find h of g of n. This is not h times g of n. This is h of g of n. So what I'm going to look to do is take g of n, which is n minus 3, and I'm going to take h of n minus 3, which just like on the first set of slides means wherever n appears in my h of n equation, n minus 3 is going to take place of n, such that this becomes the new function. So it's 3 times n minus 3 quantity squared minus 3. So just to write out a second step after this, I'm only going to do this once. This is n minus 3 times n minus 3. So when it comes to foiling or distributing, it's not just n squared minus 9. In fact, that's not really close to the answer. It's going to be n squared minus 3n minus 3n. That's minus 6n. Negative 3 times negative 3 is plus 9. So that ends up being the result of that. Make sure you expand before you distribute the 3. Now we can distribute the 3. We'll get 3n squared minus 18n plus 27 minus 3. So h of g of n equals 3n squared minus 18n plus 24. This is number 11. Number 12, find g of f of n, given g of n and f of n here. Okay, exact same thing as last time. This is the same thing as g of f of n. And I really spaced that out to make sure that you understand this is its own entity here. F of n is negative 3n cubed plus 5n squared. So we're going to take g of negative 3n cubed plus 5n squared. So the thing that will take place of n in g's equation is 3 times negative 3n cubed plus 5n squared. This is taking place there, minus 1. Now, one thing to note here, because I don't know if we're going to run into more problems with this afterward, g of f of n is not the same thing as f of g of n unless these two functions were inverses of each other. So I distributed the 3 here, and I got these two numbers here, and minus 1. Looks like nothing else can combine. Looks like that's the final answer that I'm seeing on this answer key right here. We're all good. That's g of f of n, number 12. Graph each equation. Number 13, y equals absolute value of x plus 4. The general equation here would look like this. Okay. And again, I'm not reteaching these things here, but just to get your statements here now, vertex would be at hk, stretch factor is a. So if we're looking at this one in particular, this is y equals 1 times the absolute value of x minus 0 and then plus 4. So your vertex here is at 0, 4, and your stretch factor is 1. Okay. So what I'm going to do is I'm going to start at 0, 4, and a stretch factor of 1 means as long as I displace myself 1 unit from x, I'll go up with the function type, absolute value. I'll go up the absolute value of 1. Because the stretch factor is 1, I'm just going to multiply it by 1. It stays like that. Over 2, up the absolute value of 2. Over 3, up the absolute value of 3, etc. This is linear in this direction. And in the other direction, you go negative 1. The absolute value of negative 1 is positive 1, so we're going to go up 1 as well. Negative 2, up 2. Negative 3, up 3, etc. Linear in this direction. Whole thing isn't linear, though, because it does bend like this, and you don't necessarily call it linear when you're saying that, but they do have linear qualities to it. It's definitely not exponential or quadratic or anything. It goes straight both ways. It stays straight both ways, but here it has a vertex right there. That's your graph. Number 14, identify the center and radius and sketch the graph. This is a conic. This is a circle. It has same coefficient, 1 and 1 right here. Not dividing by anything right now. Both variables are squared, and the sign in between is positive, as this is also a positive here. This is a circle. So, and also they talk about radius. The center is at 4, 4. Again, it's the opposite, x minus h, y minus k. And the radius, r squared is 4, so r is 2. So I'm going to start at the point 4, 4. And for my drawing here, I'm going to go 2 to the right, 2 up, 2 left, and 2 down. The 4 best points I can find for this circle here. Ordinarily, you would just draw this. I'm going to use my circle tool right here and be able to do it. Going out like that. And nice looking circle. If that's the graph they're looking for, that's what we got. Number 14. Number 15, sketch the graph of each function here. We have an exponential function, y equals 1/2 times 1/2 to the x power. This is y equals a times b to the x power. There could be a minus h and plus k here. These are shifts from our starting point. Your asymptote would be featured at y equals k. So in this particular instance, we're looking at y equals 1/2 times 1/2 to the x minus 0 power plus 0. So our asymptote will be at y equals 0. So I'm going to do this one actually in green this time. It's got to be a little brighter here. I'm going to start at y equals 0 here and draw this horizontal asymptote, boom, just like that. Now, when my exponent is 0, so basically h is 0, so when x is 0, the y value will be a units above point k. So my a value is 1/2. When x is 0, I'm going to be 1/2 up from k. That's a starting point for me. I'm using these numbers here without a table to make this happen. And actually, I'm going to go up one a little bit here. I'm going to change my scaling. I'll change the scale so this is 1, 2, 3, 4, etc. I don't know if I'll really need other points after that, or I want to show this mark here a little better. I'll do the same thing going to the right and left. Let's go 1, 2, 3, 4, etc. You don't have to do it this way, but I want to try and get more points that I can. So for instance, when I go 1 over here, I'm going to go 1/2 up. Excuse me. Now my b value is what I'm looking at. B is the growth factor. This 1/2, every time x increases by 1, you become 1/2 of what you previously were. Actually, I'll do this in red. Boom. So 1/2 of 1/2 is a quarter. Half of a quarter is an eighth. Half of an eighth is a 16th, etc. Gets lower and lower, never actually becomes 0. Gets close enough. You go over to the left one, you're going to divide by 1/2, which is multiplying by 2. So double 1/2 is 1. Go over 1, double 1 is 2. Go over 1, double 2 is 4, etc. And if I could fit more, I would. 8 would probably be way up here. Your graph, at least in a zoomed in look, I don't know if I can do this right. Your graph in a zoomed in look will look somewhat like this right here. It's going to approach. You know that I'm all about the half arrow here. Keeps going, but kind of has a stopping point, sort of. Has a point that it converges at right there. There's our graph. Number 16, y equals 1/2 times 1/6 to the x power. Look, they're not really doing us any favors by giving us the numbers that they are. These fractions will lead to very asymptotic values down here, which isn't going to help very much. This is y equals 1/2 times 1/6 to the x minus 0 power plus 0. So back at it again, right here, horizontal asymptote going like that. This time, just to not waste too much time, I'm actually just going to leave the scaling as is. 1, 2, 3, 1, 2, 3, etc. So when my exponent is 0, so when x is 0, I'm going to be 1/2 a units up from my asymptote. Right here, there's a starting point. Now we're going to go, every time x increases by 1, you'll be 1/6 of what you were before. 1/6 of 1/2 is 1/12. I'm already so low down here that I really don't think I can add many more points over there, if any at all. I'm just going to leave that one there and just pretend like I could fit 1/72 down there somehow. To the left side, instead of multiplying by 1/6, I'll divide by 1/6, which is multiplying by 6. 1/2 times 6 is 3. 3 times 6 is 18. As you can already tell, we'd be way up here for the next point. So this exponential function is very, very sharp. Goes down very sharply here. Say it crosses through right there. And has this curve about it. And very, very low right there, already approaching the asymptote. Sharp up the other way as well. By the way, these domains for exponential functions are all real numbers. You can plug in anything for x and get something for y. Range is limited to y is greater than 0 in these two cases. Sketch the graph of each line. This one's actually linear, x to the first, y to the first. So in terms of sketching this graph, I have two options here. I said I wouldn't do too many two-option things, but I do want to give you both because this is already written in standard form. This is 1x minus 2y equals -2. And as such, you can use standard form and find the intercepts very quickly and go off that for your graph. Your y-intercept is when x equals 0. So when this is 0, this goes away. You get -2y equals -2. Divide by 2, you get y equals 1. So there's a point on your graph that's 0, 1. I could just graph that, boom, like that. Likewise, we can find the x-intercept by substituting 0 for y in this equation. When y equals 0, this goes away. You're left with 1x equals -2. So x is -2 is your x-intercept. 2 points give you a line. You could draw the line just based off those 2 points right there, and you'd actually be set. I'm going to fix this so it's a different color. But you'd actually be set. Boom, there's your graph. In case you wanted to do it some other way, like y equals mx plus b, I'll go ahead and do that next. Let me delete all and do the same thing. Only this time, let's get y by itself. -2y equals -x minus 2. Divide by -2 everywhere. Y equals positive 1/2 x plus 1. So starting at 0, 1, we can rise 1, run 2, and collect a bunch of points. As you can see, we're on the same path as we were last time, as we should be. Should be the same line. Down 1, run 2 to the left gets me that x-intercept as well. So it's not that one's faster than the other in this case. They're both kind of the same. Still the same line. You only need 2 lines. Oh boy. You only need 2 points for a line, but it's always good to have more for the sake of precision, especially if you're going to try to find the point of intersection of two things that aren't really close to the y or x-intercept. Number 18, sketch the graph of the linear inequality right here. Y is greater than 3/2 x minus 4. Okay, I'm going to start off with the boundary line. The boundary line is the line that represents this right here. Because we are in slope-intercept form, there's really no reason for me to shy away from it. Start at 0, -4 for y-intercept and rise 3, run 2. Up 3 over 2, up 3 over 2, and so on and so forth. Now this is called a boundary line. This boundary line represents that I will either be shading above or below this to represent all of the possible solutions for this line. And as it's a greater than and not greater than or equal to, this line will be broken, dashed, dotted. It will not be solid right here. That means any points on this line are not considered to be a solution of this. Okay, so I've taken care of the boundary line. Now I want to look at this greater than thing. I am comparing my y value that I want to plug in to some x value and the y value I get as a result of it. For example, if I test the point 0, 0, what I'm asking myself is the y value for 0, 0 greater than the y value I get when I plug in 0 for x on this side? The answer is yes, as you can see right here. 0 is greater than 0 minus 4. This is true. If this point here is true, any point above the shaded line will also be true. So as that one's true, so is everything else. I'm going to be shading above, and my solution set will be all of those points right here. Anything here is true, not on the line, not below the line. So it's not about right versus left when I'm comparing y. It's about, up versus down, above versus below when comparing y here. Not really needing for me to shade all this, but I'll do it anyway. Your final solution set. And I haven't been looking at my answers lately, but I'm sure this is what it is. Yes, it is. Your final solution set should be the shaded set right here, including 0, 0. I would most often test 0, 0. It seems to really clean up your points most often. But if the boundary line's on it, heck no, I'm not going to do that. Number 19, identify the domain and range of each, then sketch the graph. Okay, to sketch the graph, the domain's really important. A log is an inverse of an exponential function. In an exponential function, the range is limited. In a log function, the domain is limited. And it has to do with what's inside here. You cannot take the log of 0. You cannot take the log of negative numbers. So this number has to be positive. X minus 2 has to be positive. X has to be greater than 2. This is your domain, which means we use this like we did in inequalities. We treat this as a boundary line, and it's vertical. X is greater than 2 means all of my points that satisfy this thing will only be to the right. Will only be to the right. Okay, good news about log functions is that if you take the log of 1, you get 0. So that's going to be 1 more than this number here, 2. So when x is 3, which is 1 over, this all becomes 0. Minus 4 is negative 4. So 1 over, when I plug in 3 for x, I'm going to get negative 4 for y. Again, because log of 1 is 0. 3 minus 2 is 1. Log of 1 is 0. Minus 4 is negative 4. After this, every time, this is an inverse of exponential. So before, every time x increased by 1, I increased my y value by a multiple of this number from the asymptote. This time, every time y increases by 1, I'm going to distance myself this many times away from the asymptote. When y goes up by 1, x will be 5 times farther away than it was last time, which is 5. And it will go 5 times farther away again, which of course I can't fit. Let's see if this one makes sense. I'm going to do this at least once here. This x value, the true x value is 7. 7 minus 2 is 5. Log base 5 of 5 is 1. 1 minus 4 is negative 3. Okay, that seems to work out. 5 times larger this way. Next one would be 25 away. This one on this side will be a fifth away. Let me use a different color. This side will be 1/5 away, and then 1/25 away, etc. Kind of hard to get all these different points here. By the way, I haven't spoken of range yet because I wanted you to see what this graph would look like. It's going to be jumping up and going over, and probably went too high on that one there. But there's the look of the graph. The domain is x is greater than 2, as that's always limited. The range will not be limited. This is all real numbers. We'll go down forever. We'll go up forever. Of course, this goes down. It never exceeds 2 for x. Number 20, natural log of x plus 4 minus 2. Well, if you have to know here, this is log base e of x plus 4 minus 2. This will kind of hamper me a little bit because I have to know how to use this constant value and get some points here. But first things first, let's go ahead and figure out what our domain is so we can begin this graph. Domain x plus 4 has to be greater than 0. It needs to be positive. So x has to be greater than negative 4. So my first line, I'm going to get this vertical asymptote here that represents I shall not pass it to the left. Again, to the left. Now, when I'm 1 away, just like I was last time, when I'm 1 away from this thing, this becomes 0. Minus 2 is negative 2. So my first point that I can find really easily is this guy right here. Okay. Now, every other point after this is based on this letter e. When I separate myself 1 away in the y direction, I'll be e times larger than I was before. If you don't know what e is, you can go to your calculator here, which is what I'm going to do. And I'm going to be using this e function. E to the first, this is a constant number. It's 2.718 something. 2.718281828, something like that. So this keeps going like this. That number 2.7 about can be fit, you know, right there. 2.7. 2.7 squared will be the next one. Excuse me, e squared. E squared, when I go 1 up again, I'll be another e times larger than I was before. So now I'll be at 7.4 about. So I'm going to go up 1, 2, 3, 4, 5, 6, 7.4. There's my next point. I can't imagine the next point I could fit even if I doubled this. Okay, so I'm going to leave it like that here. 1 over e, 1 over 2.7. Okay, it's a little less than 1/3. Excuse me, more than 1/3. So okay, about there, and you know you're getting your points a little generally at that point right there. So finishing this graph here, let's get this curve. All log graphs kind of look the same, of course, but they do change their sharpness. This one's less sharp, significantly so, than the 5 one over here. Even if you can't tell, it is. It won't grow quite as largely. Thank you, Mr. Calculator. I will now send you away, and I might deal with you later there. Domain is x is greater than -4, and just like last time, your range will be all real numbers. And there's your graph. Number 21, identify the vertex and axis of symmetry of each, then sketch the graph. Okay, I have 2 ways to find this vertex here, and I keep saying I'm not going to do 2 different ways. But in case I don't cover the other way ever again, I do have to make sure it is covered for this. One way is by completing the square here. Means find a blank here that's going to give this a perfect square trinomial, and then subtract out what I add in. Taking this number, we divide it by 2, which is 2. We square that number, that's 4. Whenever I add, I subtract to keep my equation balanced. This here is a perfect square trinomial that's represented as x plus 2 quantity squared. -1 minus 4 is -5. Now the reason for this is vertex form of a graph. Y equals a times x minus h quantity squared plus k. Your vertex is at h, k. So your vertex here, it's a 2. Your vertex here is at -2, be careful, -2, -5. That's one way of finding my vertex. I'm going to put it there and there. And I'm going to leave this equation here as well. Another way I could find my vertex right here, I'll use green, is there's a relationship, and you'll really learn it in calculus, like the reason why. We did it once, but you can prove it in calculus. There's a relationship, that's -b over 2a. The x value for the vertex occurs at -b over 2a. b is 4. So this will be -4 over 2 times a is 1. -4 over 2 is -2. So there's the x value of the vertex. The y value comes in by substituting -2 for x. And apparently, you get -5. That's 4 minus 8 minus 1 is -5. So that's the second way of getting the vertex right there. Once you have your vertex, the rest is based on the stretch factor here, 1. Stretch factor is 1, as this is a squared function. If I go over 1, I'll go up 1 squared times 1. Over 2, up 2 squared, which is 4 times 1. So standard parabola here, 3, 9, that's 3 squared. And 4, 16, I can kind of fit this. It'll be way up here at 11. -5 plus 16 is 11. And reflect across this axis of symmetry, which, by the way, I also do have to label, find the axis of symmetry. Or I have to tell you what it is. So I'll get these points here first, kind of get the curve going. And how do I find these points so quickly? Well, they are reflecting across that axis of symmetry. You know, parabolas, like absolute values, they have this mirror image about themselves that are, the mirror is like a vertical x equals equation, and it goes through the vertex. Okay, if I drew this perfectly, this would really be a mirror image of itself. The axis of symmetry is this guy that's going up and down right here. Probably do a different color there. It's going up and down right here through the vertex, and the equation of the line is what we need for the axis of symmetry. In this case here, it's going to be x equals -2. There's the line for the axis of symmetry right there. That's the line for the axis. On my wrong sheet for my paper here, so I got to go this side. Let's see. What number am I at? 21. And that works out. Okay, all good. There's your answers. Okay, 22. This one's already in vertex form, so I won't be expanding in standard form for any particular reason. I'm just going to go ahead and keep it as it is. But I will rewrite it just shortly so that I can get what the y value is of the vertex. Stretch factor is a -1 this time. This is x minus 5 quantity squared plus 0. So my vertex is at 5, 0, x minus h. So going 5 over, 0 up or down, boom, there's the vertex. Stretch factor is -1. So instead of 1, 1, 2, 4, 3, 9, I'll do 1, 1, but this time I'm going 1 down. I'll do 2, 4, but going 4 down. 3, 9, going 9 down. It's a negative. Upside down parabola. Boom, 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 reflecting across that axis of symmetry, which I have yet to draw. These drawings will probably take the longest because I can't use my... I can't draw in computers very well here. Sorry about that. Because I don't get to put my, like my finger right on the screen or anything like that. It's not as good looking. Axis of symmetry here, going up and down from here. That line is x equals 5. AOS, it's x equals 5. Good to go. Sketch the graph of each function. This is a cubic function here. Now, when it comes to a cubic function, look, this isn't in any perfect cube form, very unfortunately so. I actually can't say much about what I want to get here. I might actually have to use a table. If this was in some sort of perfect cube form, like x minus h cubed plus k, I could tell you really everything about this graph that you'd want to know based on this stuff here, but it's not in that perfect form. We're not dealing with something like that. So I'm going to have to use a table, really. But one point that I do know for sure is going to be 0, 5, because that is still the y-intercept. Okay, so x, y. I know that 0, 5 is actually one of my points here. Right there. So let's plug in some other points here. This is one of the only times I'd use a table. Now look, you could use a graphing calculator if this is on a graphing calculator portion. Let's get a few numbers here and see if any of these things actually do pop up on our graph. 1, 2, 3. Okay, so this guy right here, 0, 5, 1. 1 cubed, so 1 minus 4 is -3 plus 5 is 2. 2 cubed is 8. Minus 4 times 4 is -16. Minus 16. 8 minus 8 is -8 plus 5 is -3. Okay, you can see how that changes. And 3 cubed is 27. 3 squared is 9 times -4 is -36. 27 minus 36 is -9 plus 5 is -4. Okay, this seems to be slowing up here. Hang on. So let's see if these are all the points that I want here. Let me keep trying with this. -1 cubed is -1. -1 squared is 1. Minus 4 is -5 plus 5 is 0. -2 cubed is -8. -2 squared is 4 times -4 is -16. -8 minus 16 is -24 plus 5 is -19. Apparently when we're going over here, it's going to be going very sharply. There's probably not much I want to do over there. So I'm going to ignore those. Let's extend this down a little bit more so we can see what other points will actually fit between -10 and 10. 4 cubed is 64. 4 squared here is 16. Minus 4 times 16, that's 64 minus 64, that's 0. Plus 5 is 5. That one seems to fit. If anything, maybe I can get one more point here. 5 cubed is 125. 5 squared is 25. Minus 4 times 25, so minus 100 is 25. Plus 5 is 30. That's not going to fit there. So the points that I can plot on here is 0, 5, 1, 2, 2, -3. Wow, this cubic's very drastic. 3, -4. 4, 5. Shoots right back up here. And 5, 30. And over here, -1, 0. And 2, -19. You might be saying, what is this graph? Like, what's going on? Well, a cubic function has the ability to do something like this, and that's exactly what we're doing here. This thing's going through and down. I was really surprised. I haven't done these problems yet, so I was really surprised at the sharpness of this thing, going like, are these numbers really lining up? I can't see the pattern, and I really couldn't for a while. And I'm going to assume here the pattern's like this. It might even go below this before it comes back up like that, just to smoothly hit these points here, or at least more smoothly. And I'm getting that right there. There's the cubic function. It's looking like that very strangely. It's kind of a tough problem because I kind of had to use a table. 24, y equals square root of x minus 4, and then plus 4 on the outside there. Again, if we're looking a times square root of x minus h plus k, this is y equals 1 times square root of x minus 4 plus 4. I guess that's kind of written like that. So you're, I still don't know if it's called a vertex, but your starting point here, because it doesn't go on the other side, but it's 4, 4. That's where we're going to start. By the way, this isn't just a vertex for vertex sake. This thing is also the end of your domain. For your domain, your number inside your square root has to be 0 or positive. So your x values you're going to choose are greater than or equal to 4. We're not graphing anything to the left at all. And everything to the right that we graph is based on our stretch factor here. Every time we displace ourselves some amount, we'll go up the square root of that. Over 1, up square root of 1. Over 2, up square root of 2. I'm not going to bother with that. Neither 3, square root of 3. 4, square root of 4, which is 2, is that one right there. These are actually already enough points right there. I'm going to start graphing this. Kind of reminds you of a log function. It's a little more powerful than one. And it doesn't go underneath at all right here. So it starts here and keeps going over. That's actually your graph. Number 25, graph each function. Okay, we're dealing with a rational function now. So for a rational function, there are a lot of critical points we're going to try and find and see what we can, factor and play with here. Okay, for starters, we can get, say, x-intercepts and y-intercept. Okay. X-intercepts, we're going to be setting y equal to 0. All of f of x will become 0 here. And look, I'm going to figure out when the top becomes 0, not when the bottom becomes 0. I need 0 over a non-zero number to become 0. So the only thing I need to make sure of is my answer that I get for here, x equals 4, which the x-intercept is 4, 0, won't give me 0 if I plug in 4 down here. Negative 4 times 4 is negative 16 minus 8. Now we're good. So this point 4, 0 exists on my graph. It's not a hole. Okay. Y-intercept, set x equal to 0. So we'll take f of 0 here, 0 minus 4 over 0, negative 4 times 0, minus 8, which is negative 4 over negative 8, which is positive 2. So your y-intercept is 0, 2. Okay, first 2 points there. Next, I want to find maybe some vertical asymptotes. Now, I already mentioned there are no holes. There's no dividing 0 over 0. But we might divide non-zero numbers by 0. So we want to figure out where our vertical asymptotes here are based on setting the bottom equal to 0. Now, look, the bottom can't become 0. But if in the case that it does, that's where your vertical asymptotes appear. Negative 4x is 8. X is negative 2. This is your vertical asymptote right here. So that's graphed right here. I'm going to make it blue as well. No, I'll make it a different color. Make it green. Okay, there's your vertical asymptote. And a couple other things we can do now that we've been really dealing with this stuff lately. Let's look at some limits. Let's take a look at what it's approaching as x approaches positive and negative infinity, as x increases without bound and decreases without bound. What you're going to have here is, excuse me, I'm not going to deal with that there yet, but you have x minus 4, not limit as equals. We'll take the limit of this of x minus 4 over negative 4x minus 8. Now here, these two constant terms mean absolutely nothing to us. They are not dominant. In this case, we're left with 1x over negative 4x. And in these cases here, x over x becomes 1. So you're left with negative 1/4. This is your horizontal asymptote right here, y equals negative 1/4. As x becomes increasingly larger, you're starting to get closer to that line of negative 1/4 for y. That's one way of finding it. If you're not certain on what we did there or how that works, another way we did this is through long division. When you do long division, your quotient is the answer to the question, what is the asymptote? And the remainder is how much you go above or below that point there. So to do this one more time here, I'm going to do this with long division. I'm going to take x minus 4 and divide it by negative 4x minus 8. Negative 4x goes into x negative 1/4 times. Multiply negative 4 by negative 4x by negative 1/4, you get positive 1x. Negative 8 times negative 1/4 is positive 2. I'm going to subtract these values. X minus x is 0. Negative 4 minus 2 is negative 6, so you're left with negative 6. The remainder here is negative 6, so your answer could also, your function could also be rewritten as negative 1/4 minus 6 over negative 4x minus 8. This guy becomes the asymptote, because no matter what x equals over here, you'll still get a non-zero value, and this will be how much above or below the asymptote you become. So y equals negative 1/4 is still the asymptote here. These are the only critical points I'm going to be finding myself, or that I can find. These graphs have this kind of behavior where it'll go above and top right in this case, because you can see the points, and then bottom right, sorry about that, excuse me, bottom left over here, it would have some mirrored points there that I suppose I could find. I'm going to refrain for now. That's going to be looking like that here. This is your rational function. Here are your features. We're good. Number 26, identify vertex and axis of symmetry of each. They do not ask us to graph this. This is in vertex form. I'm going to do this very quickly. Your vertex is at 2, 8. Your axis of symmetry goes on the vertex. This parabola goes up and down as your axis of symmetry does at x equals 2. It's your x equals h. H is the axis here. Right here, doesn't matter what that stretch factor is either. This vertex is at 4, negative 3. Your axis of symmetry is at x equals 4. They did not ask us to graph. I'm not going to be graphing. Thank you. Oh, sorry, that's 27 is the next problem here. Let me write that one more time. Vertex 4, negative 3, x equals 4. Boom. There we go. Number 28, graph each number in the complex plane. Now, one thing, I copied this over that has x and y in it. This shouldn't say y, it should say imaginary. This is your imaginary axis. This is your real axis. Think of them like a number line, you know, just a regular number line like this that we see. This is your normal real number line, okay? And then your imaginary one splits off. Whoops. Your imaginary one splits off based on that right there. So, real and imaginary here. Let's go ahead and plot this. The real number is negative 4. The imaginary number is negative 1i. That point is plotted right there. And that's it. Just got to graph it. If they asked you to find the distance here, you'd use Pythagorean, the absolute value of, you'd find the distance from 0 by using Pythagorean theorem. That answer would have been square root of 17. Number 29, negative 1. This is negative 1 plus 0i. Don't confuse yourself too much with what you're being asked for. The imaginary value here apparently is 0. You're not going up and down at all. You're just going left 1. So negative 1, there's your point. That is also 1 away. The absolute value of that is 1. Simplify. Here are a lot more complex numbers. By simplification, they're asking for you to write this in the form a plus bi. So have these things separated. Do the best you can there. So number 30. Number 30, what I'm going to do is distribute. Distribute. Boom, 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 boom. Foilage. 2 times negative 1 is negative 2. 2 times 4i is 8i. Negative 1 times 4i is minus 4i. 4i times 4i is 16i squared. I squared is negative 1. These two combine here. Negative 1 times 16 is negative 16. Negative 2 minus 16 is negative 18. We're left with negative 18 plus 4i. That's your a plus bi form. Number 31, negative 8 times 7i times negative 4 plus 4i. You can distribute this any way you want here. I'll start with the negative 8, I suppose. Negative 8 times 7i is negative 56i. So we got negative 56i times negative 4 plus 4i. Notice here when you distribute, this becomes imaginary together. These actually become I squared, which will become real. Negative 56 times negative 4 is positive 224. So we got 224i. Negative 56i plus 4i is negative 224i squared. I squared is negative 1. Negative 1 times negative 224 is positive 224. Let's go ahead and write that one first, as that's the real component. And plus 224i. Let me make sure those numbers are right. Yes, it looks like they're fine. And we are set to jet. Okay? Number 32, 3 minus I minus the quantity negative 1 minus 4i. So these are two different complex numbers here, and you'll often see them written like that, where they have the parentheses. We're going to distribute the negative here. Negative times a negative is a positive. Negative times a negative is a positive. Both will be pluses in this case here. 3 plus 1 is 4. Negative I plus 4i is 3i. There's a plus bi form for 32. 33, negative 2 minus this quantity. Again, I'll distribute the negative, then plus 8. Let me do negative 2 plus 8 first. Negative 2 plus 8 is 6. 6, we're going to do minus negative 5, so plus 5, minus positive 4i, which is minus 4i. 6 plus 5 is 11. 11 minus 4i is your result. That's 33. 34. Now, this is not yet written in that form. Again, I want to separate my a and bi. Now, you are not going to write this as like this, a plus bi like that. No, nothing like this works. You can't split up a denominator like that. This division doesn't work. But what you can do is you can get your whole, you can get a common, well, it is common. You can get a real number denominator. That way you can split these two things up in a more proper fashion. To do so, we're going to multiply by this guy's conjugate. Negative 3 plus 5i over negative 3 plus 5i. Now, the good thing about the bottom here, when you FOIL something like this will become, you know, a minus b times a plus b is just going to be a squared minus b squared. So this will become, on top I'm going to distribute. I'll do that actually last. On bottom, though, negative 3 squared is 9. We're going to do minus negative 5 negative 5i times 5i is negative 25i squared. Okay. Now this thing will clean up even better with imaginary numbers that you'll see. Here I have to distribute though. Negative 4 times 3 is 12. Negative 8 times 5 is negative 4 times 5i is negative 20i. Negative 8i times negative 3 is plus 24i. Negative 8 times 5, negative 8i times 5i is negative 40i squared. That's an I. These two combine on top. The negative 20i plus 24i, that's a 4i. And this becomes 12 plus 40, so that's 52. 52 plus 4i divided by. This becomes a positive 25. 9 plus 25 is 34. So you're going to be left with, if I split this up here, which, well, you know what? This doesn't split it up. So I'll give you a split up answer after. But what I do have is a common factor of 2 on top that I can divide with a common factor of 2 on bottom. So the 2's cancel here, and you're left with 26 plus 2i over 17. You could, if you did a plus bi totally separately, 26 would be over 17, 2 would be over 17 times I. Either of these answers are appropriate. This is a little more so a plus bi form for real number, imaginary component right there. But this is the answer you see on the key. And there you go. 35, same idea here. We have a complex number on the bottom. We're going to multiply by its conjugate. Hopefully we can be a little quicker on the bottom here, which we were pretty quick last time. This will be, technically just becomes a squared plus b squared. And your b value here is 1 and 1. So this becomes negative 6 squared is 36 plus 1 squared is 1. That's all it becomes. On top, 6 times negative 6 is negative 36. 6 times negative I is minus 6i. Negative 5i times negative 6 is positive 30i. Negative 5i times negative I is positive 5i squared. So on top, what combines here is negative 36. This will become minus 5. That's a negative 41. Negative 6 plus 30i is positive 24i. This is all divided by 37. Shame nothing can cancel or, reduce and simplify. Otherwise, the numbers, sometimes you got to question them. But that is your final answer there. Another way we could write it is like this. Okay. But answer key would reveal that, and it does. Last one in this set, number 36, negative 6 plus 4i over 3i. This still remains the fact that this is an imaginary number. It's still 0 plus 3i. So I'll multiply by negative 3i, 0 minus 3i over 0 minus 3i. Does it have to be negative? No. But in this case, you'd probably prefer it because I'm going to get a positive denominator as a result, and I'd prefer that over not. This will be over, see, this is negative 9i squared. This is negative 9i squared. And what's going to happen here is that going to be a positive 9, right? I squared is negative 1. So when you do negative 6 times negative 3i, that's a positive 18i. And then negative 3i, 18i. And then negative 3i times 4i is negative 12i squared. Negative 12i squared is a positive 12. This will be plus 18i. Everything here can be, there's a factor of 3 I can pull out on top and bottom here. So I'll be left with 4 plus 6i here, and on bottom I'll have a 3. So 4 plus 6i over 3 is your result, or 4/3 plus 6/3 I, which is 2i, is another way of writing that answer there. Both of them would work. On the answer sheet, 6i is written first for some reason. I like the real number written first. Solve each equation by factoring. Okay, now we're dealing with quadratics here. They ask by factoring, so I won't use complete the square or quadratic formula. Let's assume that these things can factor out. In order to factor, we do have to set this thing equal to 0. Solving by factoring also means solve using zero product property, which means the right side has to be set equal to 0. This needs to factor down in something. This is a 1n squared, so all I need to do is answer the question. The two numbers that multiply to positive 8 and add to negative 9, your factors of 8 are 8 and 1, 4 and 2. Product positive, sum negative means both numbers negative. Negative 8 minus 1 is negative 9. Apparently, those are your numbers. Negative 8, negative 1. This is all set equal to 0. Zero product property states if one element times another, one quantity equals 0, one of these sets has to be 0. Either this or this. And as long as one's 0, the whole result would be 0. Either n equals 8 or n equals 1. Woo! Number 38. Same idea as last time. Let's get this in standard form, get everything on one side of the equation, set it equal to 0, factor, and solve using zero product property. Add 9x to both sides. The question here becomes, as it's a 1x squared again, what two numbers multiply to become 20 and add to become 9? 5 times 4 is 20. 5 plus 4 is 9. Let's not beat around the bush here. Let's go ahead and write that in already. Right? You factor however it is you need to, of course. I'm giving you the process that would make this quickest here. Your other numbers could have been 20 and 1, 10 and 2. None of those would have added to 9. Either x equals negative 4 or x equals negative 5. All right, solve them by factoring. Nicely done. These are also your x-intercepts, as were number 37. Approximate the real zeros of each function to the nearest tenth. Okay, when they're giving us these kinds of numbers here, we're talking about real zeros, by the way, not imaginaries, to the nearest tenth, I think we're using a graphing calculator if they're asking about that. Maybe this is factorable. Actually, it looks like it's not. Maybe you can get real zeros another way. They're asking us to approximate. I'm going to go with their flow here. Let's go ahead and figure out what this is going to be. X to the fourth. We'll do minus x squared plus 2. And to approximate zeros, basically what I want to do is find this thing on my graph. So go to the graph, see where our graph is. Well, there it is. It goes down and back up. I don't think it ever actually hits the x-axis. I really don't. And as you know, it's a quartic function. It goes down and it barely goes back up here, but it does. I'll show you here a little more closely. Get a little closer here. And this goes down and back up very slightly. Boom, down, up, down, up. Now, a quartic only has the ability to have 3 relative extremes. These 2 relative mins and this relative max is all it can do. In other words, if I did zoom out and I wanted to keep zooming out to see if it would ever go back down again, it won't. You won't? It won't. It will not. It's going to stay just like that. So it never hits the x-axis. Those are your zeros. It never hits the x-axis. That means there are no real zeros. All of your zeros are complex numbers. If you're not for sure, hit second calc, go to zeros here. Left bound, right bound. Yeah, let's go to the left a little bit. Woo! And right bound, let's go to the right here. And again, I know that it's only going to exist between here and guess, because we're going to have to do this later. And it's thinking, and it's hanging up. No sign change. It means it's never going positive to negative or positive to 0, anything like that. So, no real zeros for this first one. It says approximate them. There are no real zeros. They're all imaginary. They're all in your head. They're all made up. There are no real zeros here. They don't ask us to find the imaginary numbers, but there are a total of 4 complex numbers there. Just like here, this is another quartic. Number 40, f of x equals negative x to the 4th. Let's go negative x to the 4th plus 3x squared plus 3x squared plus 3x. Let's hope this one has zeros. Otherwise, this is kind of a, a set of problems that's like minus 1. Let's go to the graph, see if we can find where they cross. Aha! So I'm seeing 2 places they cross here. I'm going to zoom in on those a little more closely. Again, as this is a quartic function, it will at most only have 3 relative extremes. There was a relative max up here, and then a min, and it popped back up here and started going down again. Here and here. Let's find out those 2 numbers. Don't assume that's a 2. It might be, but don't assume it is. Let's find it out for sure. Let's find our zeros. Left bound. Let's get to the left of this first 0 over here. Right bounds, go to the right of it. Guess, I'm just going to guess now. They'll give me a number, say round to the nearest 10th. X equals 2.648, etc. Excuse me, 0.2. So one of your answers rounded to the nearest 10th is x is 0.3. Let me do the approximate symbol here. X is about 0.3. Rounded. X is about 0.3. That's one of your answers there. The second answer, let's find the other 0. Second calc, 0. Let's go left bound, sure. Right bound, let's go this way. It's going to go up and down. Right there. Let's get to the right of it. There to the right of it. Guess, give me that point. 2.055. So it was very close to 2. Obviously, we could see that. But not even rounded to the nearest 10th is it 2.0. No, it's 2.1. So those are your 2 answers there. Those are your approximated x-intercepts. So 0.3 and 2.1 are your real zeros. As this is a quartic, there's a chance of 2 imaginary zeros there as well, of which they're not asking us to find. And if we did, it would take some time. Oh, 40 should have been over here. I'm sorry, but you still know the answer there. Okay, 41, find all zeros. This time they're saying find them. I guess you could use your graphing calculator, but when they say something like that, it's likely that there might be other things to do. Even for this big problem here, it's likely there are some other things you can do to find them. I'm going to find them a more conventional way. There's a common factor of x here, which means if I factor out an x, then I'm left with 3x squared. I'm left with a quadratic. And as we know, we can solve quadratics in our ways, right? We have our ways, don't we? Let's set this all equal to 0, by the way. Setting y equal to 0, let's solve for x. Well, zero product property states that if one thing times another equals 0, either this equals 0, which is one of your zeros, or this equals 0. And let's solve this like we would a quadratic. First, let's see if this is factorable. In order for this to be factorable here, there would be 2 numbers. Well, let me first test if it's factorable. -1. Yes, this should be. So here's the factored form, +1, -1. If you use kind of the diamond rectangle stuff or A dot C and B and whatever different things you do here, I have a 3x squared here, a -1 here. And you know what? I'm not going to be doing this one often. If you have your own means of factoring, please do so. I'll do it this one time, but after this, I will not. Find the two numbers. 3 times negative 1 is negative 3. That's a dot c, or a times c. And b is 2. Two numbers that make up this scenario right here. That's 3 and negative 1. So we got a 3x and negative 1x. You can also do this with what's called factoring by grouping, which we're going to do on number 42. 3x here, a 1x there. 3x times 1 is 3. X times negative 1 is negative 1x. We're up to 3x minus 1 times x plus 1 equals 0. And again, factoring by grouping is the same kind of idea. I'll leave it to this for now. We also could have used quadratic formula. Technically, you could have also used completing the square. I don't really think that's one you'd be using for this problem, neither would I. 1/3 is another 0 here, and negative 1 is the third 0. The one thing I'd caution you with, if you did use your graphing calculator, you found a real 0, it would say 0.3 repeating. Maybe you'd know that 0.3 repeating is 1/3, hopefully you do, but please don't be writing 0.3 repeating as an answer there. We want exact ones. Let's get them whenever we can. Number 42, what I'm going to do is use what's called factoring by grouping here. What you want to test at times is see if you can get pairs of numbers that share a common factor. And within your end hope here, like these both have a factor of 3 x's, we can take out 4 x's, x to the fourth. And the hope is that the thing inside the parentheses exists as a common factor for all of these different pairs that you're factoring something out. 35x squared can factor out of here. You're left with 3x plus 2. See at 3x plus 2, 3x plus 2. This has a factor of 72, and you're left with 3x plus 2. Take a look at that. This all equals 0, by the way. Now, what happens here is this is a common factor in all 3 sets here. So we factor that out, and what's remaining, here's 3x plus 2. What's remaining is all these 3 terms here. 3x to the fourth plus 35x squared plus 72. And this is all equal to 0. So either 3x plus 2 equals 0. Let's get this one first, in which case 3x is negative 2, so x is negative 2/3. That's one of your answers. By the way, how many can we possibly get here? 5. Or 3x to the fourth plus 35x squared plus 72 equals 0. Now, 3 is not a common factor of these numbers here, unfortunately. But if this one equals 0, what I'm going to do is see if this is factorable. I'm going to test it for myself here first. I might, sometimes these numbers get rather large. It is kind of hard to come up with your answers here, in this case, when you're doing something. But one thing I'm doing with factoring here, I'm going to let a equal x squared, okay? And I'm treating this like a quadratic, basically. 35a plus 72 equals 0. I have to still solve for x, but I sure hope this is factorable. Otherwise, I'll have to go to completing the square or quadratic formula. Likely, I'd try quadratic formula. If this is factorable, this would be 3a and a. I have to try factors of 72, like 12 and 6, 18, 12. No, that one's not going to work. 36, no, not that one. 72, 9 and 8. Times 9 plus 8, 26. Yes, that one works. So 3 times 9 is 27. 1 times 8 is 8. 27 plus 8 is 35. So this will factor into this here. Again, use your own way of factoring that you know of. Please use that as such and then work it out. Now, I used a for what I needed to do. Perceive this as a quadratic to factor. You never have to do that, but it is something that you are allowed to do. I'm going to let x squared come back into play here, and I'm going to attempt to solve. Now, these numbers, these answers don't look like they're going to be real number answers. Zero product property will show you here that you're going to be taking the square root of negative numbers. X squared is negative 8/3, so x will be plus or minus the square root of negative 8/3. Now, we can keep going with this, and we will. For starters, I'd like to rationalize these. Okay, plus or minus square root of negative 8 divided by square root of 3. First, I'm going to begin by rationalizing the denominator. That'll be plus or minus. By the way, in I, I can dump an I out of the 8 here. 8 times 3 is 24, so this is I root 24 over 3. Now, root 24 has a perfect square factor of 4 in it. Root 4 times root 6 is 2 root 6. This will be 2i root 6 all divided by 3 here. Plus or minus 2i root 6 over 3. That's your final set for x there. Your other set right here, x squared plus 9, this is probably the easier one. X squared plus 9 equals 0. So x squared is negative 9. So x is the square root of negative 9, plus or minus square root of negative 9. Square root of 9 is 3. There's an I involved as well, plus or minus 3i. So your 4 answers here are x equals, you see me, your 5 answers. X equals negative 2/3 plus or minus 3i. Those are 2 answers. And then plus or minus 2i root 6 over 3. Those are your other 2 answers. Now, this does mean this only crosses the x-axis once, but they ask us to find all zeros, real and imaginary. I did not once use quadratic formula. I did not once use my calculator. I got these answers in exact form. This is a way that you're expected to know what to do, how to do it. State the number of complex zeros, the possible number of real and imaginary zeros, and the possible rational zeros for each function. Then find all zeros. Number 43. Okay, there's a lot to do for these problems here. First of all, for 43, number of complex zeros is all the zeros total. Number of complex zeros, there are 3. Right? There are 3 of them. You know, we're dealing with a cubic, so 3 complex zeros. I'm going to do some work over to the right. I'll try and do that for every problem here. Let's find all the other zeros here. This is x. You know, I'm going to do factoring by grouping to start off with already. You can see that x cubed plus 5x squared has a common factor of x squared. You're left with x plus 5. And technically, if I factor out a 1, I'm left with x plus 5 over here as well. This is all equal to 0. So now x plus 5 is a common factor in both sets here, and left inside is x squared plus 1 from these 2 parts right here. This is all equal to 0. So if you can tell from right now, this is going to give you a real 0 of negative 5. This is going to give you complex zeros of plus or minus I, right? X squared is negative 1, x is plus or minus. Now they did ask us, you know what? I probably should have worked with you a little more here. Possible number of. Let me tell you about this possibility thing, because I know we haven't talked about that before, really, very much. Possible number here. Before I got those answers, okay, this is before I did this. Your possible number, you could have 3 real and 0 imaginary. You could also have 1 real and 2 imaginary. And I think that's it. So, or you could have 2 real, 0 imaginary if the 2 real, one of them has a multiple of 2. One has multiplicity of 2. Unfortunately, unless or until we do drawings with the stuff, I don't want to teach this stuff like I said, but these are your answers. First of all, imaginary numbers come in conjugate pairs. You can see here, plus or minus I. We saw plus or minus 3i before, and we saw plus or minus 2i root 6 all over 3. They come in pairs. So there's going to be an even number of imaginary numbers, no matter what you do. 0, 2, 4, whatever they are. And then 3, it could be 3 because for cubic, 3 plus 0, 1 plus 2. This one could have a multiplicity of 2, which means if you have the same number appear twice as an answer, we'll see if we run into those. We haven't yet. Possible rational zeros for each function. Then find all zeros. So by the way, I did this part earliest. I should have done it last. My apologies. Possible rational zeros for each function. They're not asking how many possible, though I could give you that. Possible rational zeros are your p over q's. That's your factors of this number divided by your factors of this number. Factors of 5 are 5, 1, negative 5, and negative 1. So plus or minus 1, plus or minus 5, over plus or minus 1. So your possible rational zeros are positive negative 1 and positive negative 5. Those 4 possible rational zeros. We got negative 5 as the only rational zero here. Okay? And here was the answer. Here was the last set of answers. Here were your zeros, your 3 zeros. 2 imaginary, 1 real. As we see, it rolls up right there. So I'll do this last, next. Number 44, number of complex zeros is going to be 5. There will be 5 complex zeros. Okay, 5 complex zeros. Possible number of real and imaginary. So you can either have 5 real, 0 imaginary. You could have 3 real, 2 imaginary. You could have 1 real, 4 imaginary. Again, going up by evens for the imaginaries. You could also have 3 real, 0 imaginary. This is if you have 2 pairs of real sets of numbers that have a multiplicity of 2. That's 2 sets. You could have 4 real, 0 imaginary. That's 1 set that has a multiplicity of 2 and all the others are real. Gosh, this is kind of hard to come up with, to keep track of all of them. You could also have multiplicity of 2 for real, then an even number. So you could have 2 real and 2 imaginary. So this would be if one of your sets of reals has a multiplicity of 2 and 2 imaginary there. So this is going to be one of our sets of answers here. Possible rational zeros for this function here, we're going to do factors of 32 divided by factors of 1. Obviously, factors of 1 are plus or minus 1. And when you divide by a positive or negative 1, all you're left with is what's on top. So I'll list those straight up right now. Possible rational zeros, factors of 32 are 1, 2, 4, 32, 5, no, 6, no, 7, no, 8, 16, and 32. These 12 are possible rational zeros, of which we could test any and all of them to find the real zeros. If they're asking you to find them here, if factoring by grouping doesn't work out, then I would do the rational root theorem. In this case here, it's going to work out. Factoring by grouping does exist here. Common factors, I have x to the 4th that I can factor out of the first 2. I'm left with x minus 2. I have an 8x squared I can factor out of here. I'm left with x minus 2. Yay. And I factor a 16 out of here. I'm left with x minus 2. This is all set equal to 0. Let's find our zeros. X minus 2 times x to the 4th plus 8x squared plus 16 equals 0. If this is the case, either x minus 2 equals 0, in which case x equals 2, or x to the 4th plus 8x squared plus 16 equals 0. If I let a equal x squared for a moment, you're looking at a quadratic that's a squared plus 8a plus 16 equals 0. And you're answering the question, what two numbers multiply to 16 and add to 8? Well, it's 4 and 4. So it's a plus 4 times a plus 4, or you can also write it as a plus 4 quantity squared equals 0 right there. So this becomes x squared plus 4 quantity squared equals 0. Okay, so, I never considered the fact that imaginaries could have multiplicities as well. There's also another fact right there. So let's see. Either x squared, so x squared plus 4 equals 0. Take the square root of both sides. So x squared equals negative 4. So x is plus or minus square root of 4, which is plus or minus 2i. Now these numbers here have a multiplicity of 2 because as we counted out, mult of 2, as we counted out here, these are 2 answers here, 1, 2, 2i, negative 2i, and then there's 2 right there. So that's gee, I didn't consider the fact that imaginaries could have multiplicities. Hello. Think of those things. So it's none of these sets so far. This was 1 real. This was 1 real and 2 imaginary. 2 imaginary. The imaginary come from both of them having a multiplicity of 2. 2i and 2i appear twice. Negative 2i appear twice. That's actually the last set. Man, gotta consider those, right? So there's that one. Number 45, x to the fourth plus 18x squared plus 81. Number of complex zeros, 4 complex zeros. It can either be broken up by, and let me try my best this time to get all these right. It could be either broken up by 4 real, 0 imaginary, 2 real, 2 imaginary, 0 real, 4 imaginary. Okay, now think of the multiplicities here. We could have 3 real, 0 imaginary. If one of my zeros have a multiplicity of 1, we could have 2 real, 0 imaginary. If 2 of them have a multiplicity of 2, you could have, let's see, you could have one with a multiplicity. Let's see, I didn't consider multiplicities of 3. Well, let's see, you can't do that because, well, yeah, you could. You could have 2 real, 0 imaginary. Oh, well, that's still 2 real, 0 imaginary. So that's why that doesn't matter. So there are different combinations of having 2 real, 0 imaginary. You could have 1 real, 0 imaginary, because 1 could have a multiplicity of 4. I don't know if I considered that last time in this problem. You could have had some sets like that. I think I did consider that. There are a lot of different sets here. Now the imaginaries could have multiplicities, right? I could have 0 real, 2 imaginary if they have multiplicity of 2. I could have 0 real, 1 imaginary if that has a multiplicity of 4. And I could have 1 real, 2 imaginary if it has the imaginaries has, no, that doesn't work. So that's it. No, sorry. They have to come in pairs, right? So I think that's it right there. Let's hope. Okay, our P over Q's, find all zeros. Factors of this divided by factors of 1. Factors of 1, once again, are 1 and negative 1, so I'm not clearly going to list those in such a way that they are relevant. I'll just list my factors of 81, such as 1, 3, 9, 27, and 81. So your real numbers can come from these sets here. Your rational solutions. So here's our set. We have to solve for our zeros here. Let's try that. X to the fourth plus 18x squared plus 81 equals 0. I'm going to save some time here. If you do the let a stuff equals, you'll do just fine here. You're going to get x squared plus 9 times x squared plus 9, which is x squared plus 9 quantity squared. That equals 0. Square root of both sides, x squared plus 9 equals 0. X squared equals negative 9. So x is plus or minus square root of negative 9, which is plus or minus 3i. There are 2 answers. Each of them have a multiplicity of 2. That is 0 real, 2 imaginary. There are no real solutions there, just 2 imaginary. Each imaginary set is a multiplicity of 2. I don't like listing these things out. Kind of takes a while. Number 46, last set, or last one right here, hopefully. There might be some others beyond this. Oh, you know what? Sorry, I just took a peek at the answer key. I took a peek at the answer key and saw that they just say either there's 0, 2, or 4 real and stuff like that, right? So they're just listing how many different possible ones that there are, But the things with multiplicities, I don't think they're accounting for. So I think I'm going to list out the sets that they can be. I'm going to stick with that. Anyway, so for number 46 here, same idea. Number of complex zeros be 3 complex zeros. And how can they be derived? Well, and by the way, I think when they're listing them out here for things, they're not including them as multiplicities. So here, they probably call this 4 imaginaries. Plus 3i, minus 3i, minus 3i. I'm saying it's 2 imaginaries, each with multiplicity of 2. Sorry about that. Keep going back and forth. Number of real and imaginary zeros. The 3 complex zeros can either be 3 real, 0 imaginary, 1 real, 0 imaginary, 2 imaginary. Of course, there will be that as well. 2 imaginary. Okay, think of multiplicities. You could have 2 real, 0 imaginary if one of your reals is a multiplicity of 2. 1 real, 0 imaginary if this has a multiplicity of 3. Your 1 real, 1 imaginary. Well, you can't have 1 imaginary, right? They have to be even. So that might be it. Okay, that's it. Because they have to come in even pairs. Okay, so there's that. Your P over Q is factors of 4 divided by factors of 1. P over Q there will be plus or minus 1, plus or minus 2, and plus or minus 4. These are the possible rational ones we'll come up with. As you can see, there have been a lot of imaginaries here, so dealing with a whole lot of imaginaries. All right, set this equal to 0, and factoring by grouping looks like it exists again, which is awesome. So we don't have to do the rational root theorem. Subtract a 4, you're left with x plus 1 inside here. Set this all equal to 0. So either x plus 1 or x squared minus 4 can equal 0 here. X plus 1 equals 0. X is negative 1. That's a real 0. Check out that one, minus 1. X squared minus 4 equals 0. X squared equals 4. X equals plus or minus 2 are your other two zeros. All real zeros, all rational zeros, all fitting within this set right here. That's 3 real, 0 imaginary. We're done. Graph each function. Great. Graph each function. Now we have some rational functions here. Number 47. We'll do it like we did the previous set. Let's find x-intercepts, should they exist. Y-intercept, should it exist. We'll find any holes, should they exist. There won't be any 0 over 0s. Vertical asymptotes, horizontal asymptotes, and then I think from there we can probably graph. X-intercept, set y equal to 0, or better yet, set the top equal to 0 because we don't want the bottom to be 0. 3 equals 0. Is that possible? No. No x-intercepts. If there was a numerator on top if the numerator had an x in it on top, then we'd use that. But no x-intercepts probably gives you a hint to something else in a moment. Y-intercept, you set x equal to 0. F of 0 equals 3 over 0 plus 1. 3 over 1 is 3. So your y-intercept is at 0, 3. It's right there. Okay. Your vertical asymptote here is where x plus 1 equals 0. That's x equals negative 1. Again, x can't equal negative 1, but the point is that's the equation of the line for that one. Your horizontal asymptote, last time I spoke of limits. This time, just think of it as division. You're going to be doing 3 divided by x plus 1. X plus 1 can't go into 3 at all, so your remainder is 3. That's just your answer. It's 0 over remainder 3. So your function is f of x equals 0 plus 3 over x plus 1. Your horizontal asymptote's at 0. As x goes increasingly larger and smaller, you're getting closer and closer to 0. So your horizontal asymptote is at y equals 0 here, going across this way. Okay. Now, I mentioned all those things given the fact that there's actually more that we can reduce, and I'm going to do that with you right now so I can explain it a little better. There's a way of doing this in a shorter form here, which is a over x minus h plus k. If you're in this form, there's kind of a shortcut to graphing. Your h and k is the point of intersection of your two asymptotes. So the h value is negative 1. That's negative 1 for x. K value is 0. That's 0 for y. That's the point of intersection of your two asymptotes. Boom. A represents a stretch factor, if you will, for however much we go over, we take 3 divided by that number. So from here, if I go over 1, 3 divided by 1 is 3. That's how much I'm going to go up. If I go over 2, 3 divided by 2 is 1.5. There's a point. If I go over 3, 3 divided by 3 is 1. So that's right here. If I go over 4, 3 over 4 is 0.75, etc. 3 over 6 is 1/2, stuff like that. And you could reflex these if you wanted to as well. 0.75, 1/2. You get a whole bunch of points right there. You get the idea. Your graph is doing something like this. Well, something like that. I'm not drawing very well. This on this side, and guess what? It only reflects on this side as well. -1, 3 over -1 is -3, -1.5, -1 over 6, down 1/2, stuff like that. All this stuff fits on the same way on this side as well. So if I run into any more of those, I'm going to try and graph them like that more quickly. But you also have to note some possible holes and stuff in the way. So I'm going to still try and come up with some of these. Number 48, x squared plus 5x plus 4 over 4, x squared minus 8x minus 12. Okay, this might help me in the future. I see this as factorable. Let's see if this will help me at all. X plus 4 times x plus 1 is on top. On bottom, if I factor out a 4, I'm left with 4x squared minus 2x minus 3. This factors down to x minus 3 times x plus 1. Okay, this x plus 1 plus x plus 1, it does cancel, yes. But x, that means if you substitute -1 for x on top and bottom, you'll have 0 over 0, which is a hole. So one of my holes is at x equals -1. Okay, if you want to find out the coordinate point of that hole, by that I mean where we're going to place it instead of the graph, you can plug in -1 into here and find out. -1 plus 4 is 3. This will be 4 over -1 minus 3. So it's going to be 3 over -16. So it's -3/16. So it's kind of a strange number there. It's not going to be something particular for us. But I'll make sure to graph a hole there. Okay, given this right here, I can kind of deal with the rest based on that. So I have x plus 4, because all I needed was that whole part. I have x plus 4 over 4 times x minus 3. I'll look at 4x minus 12 again. I might need to use that to help me better. Okay, x-intercepts. Set x plus 4 equal to 0. X plus 4 equals 0. X equals -4. So there's a point, -4 comma 0. I'll plot it right there. This will not be a hole. We already found our one hole. So we don't have to deal with x-intercept stuff anymore like that. Y-intercept, set x equal to 0. We'll do f of 0 equals, and 0 plus 4 is 4. 0 minus 12 is -12. That's -1/3. So there's a y-intercept of 0, comma -1/3. That is right there. Vertical, horizontal asymptotes. Vertical asymptote, find out what values in this thing we can't let be 0 by setting it equals 0. Vertical asymptote, 4x minus 12 equals 0. 4x equals 12, x equals 3. That's the equation of the line for the vertical asymptote right there. It's going to be right, +3. It's going to be right here. Okay. Horizontal asymptote, I'm going to do my long division here. Again, if you know limits, you can work on it that way. I expect an answer of 1/4. Y equals 1/4, by the way. So we're going to do x plus 4 divided by 4x minus 12. 4x goes into x 1/4 of a time. 4x times 1/4 is 1x. -12 times 1/4 is -3. Subtract both. X over x is 0. 4 minus -3 is 4 plus 3, which is 7. It's 1/4, remainder 7. So your equation can also be rewritten as f of x equals 1/4 plus 7 all over 4x minus 12. This is the horizontal asymptote. This is the remainder, how much you'd be going up and down based on that. I'm going to kind of leave that be, and I'm just going to get this remainder going, and then we'll kind of draw the graph based on what we see here. So 1/4 here going across. Let's say that's good enough right there. And then, I'm not going to plot any more points or bother with any more here. At this point, we kind of understand our graph will be on opposite sides of this thing. As long as it's kind of got that linear idea, there's not going to be a reason to not believe it doesn't do something like this. So kind of close enough. My drawing's kind of bad, but we're getting the drawing in, right? Getting the drawing in. I have to find another page here. Okay, so that was number 40. What was that, 48? That was number 48. Number 49, f of x equals to do on top and to do on bottom. Okay, what I first want to do, again, is find those holes by factoring this, writing this out another way if it is factorable. Looks like top's factorable. Bottom, I can factor out a negative 2. I'll be left with x plus 3. Oh, you know what? Last problem. I forgot to put a hole in. X equals negative 1, right? So there would be a hole somewhere, wherever this crosses at negative 1, there'd be a hole there, right? We'd be doing that. Excuse me, negative 1, not positive 1. Where was I going? Oh, I was going 1 to the left. Excuse me. There'd be a hole right here. So there's a jump in my graph. I'm sorry. Goes back to it. But anyway, this one doesn't have a hole. There's nothing that's going to cancel where we're going to get 0 over 0. So factoring was okay for us. It probably helps us finding the x-intercept a little bit because x-intercept, we got to set y equal to 0. And we're going to see when the numerator equals 0. So we need to know when this equals 0. Factoring it helps. We can see that x equals negative 4 is an x-intercept and x equals 2 is an x-intercept. So negative 4, 0 and 2, 0. Let's graph those right here. Negative 4, 0 and 2, 0. Okay. Now this is the first time it's crossing two x-intercepts, which means it definitely doesn't have a horizontal asymptote at 0. Let's see what else this graph does. Y-intercept. Y-intercept will set x equal to 0. 0 plus 0 minus 8 over 0 minus 6 is positive 4/3. So your y-intercept is at 0, 4/3. So let's get that point. 1 1/3. About right there. Okay. Z-intercept. There is no z-intercept. Vertical asymptote. Vertical asymptote set bottom equal to 0. Negative 2x minus 6 equals 0. The equation of this line will be the vertical asymptote. Negative 2x is positive 6, so x is negative 3. Vertical asymptote at x equals negative 3. Let's get that drawn. Okay. Horizontal asymptote. Now, what I'm seeing right here is something I already know is going to change this a little bit. You either will have horizontal, possibly, you'll either have horizontal asymptote or a slant asymptote. So let me put horizontal asymptote slash slant asymptote. A slant asymptote is when your quotient, when the thing you divide is linear instead of constant. So when we do this division, we're going to do quadratic divided by linear. The result is going to be linear. And if you've done more with limits, you might already know what this answer is going to be approaching, but let's do our long division just in case. X squared plus 2x minus 8 divided by negative 2x, divided by negative 2x minus 6. Okay. Here we go. Negative 2x goes into x squared, negative 1/2 x times. Negative 2x times negative 1/2 x should be positive x squared. Good. Negative 6 times negative 1/2 x is positive 3x. Okay. Subtract cancels. 2 minus 3 is negative 1. So this is negative 1x. Bring down the 8 minus 8. We're going to do this division again. One more time. Negative 2x goes into negative x, positive 1/2 times. Negative 2x times 1/2 is negative x. Negative 6 times 1/2 is negative 3. Subtract negative 8 minus negative 3 is negative 5. Remainder negative 5 means our function could also be written as negative 1/2 x plus 1/2 minus 5 all over negative 2x minus 6. Like that. Crazy, crazy, crazy looking number right there. But this is your slant asymptote. Graph this like y equals negative 1/2 x plus 1/2. So that graph will give us, the thing that we're looking for there. So it's going to be starting at 1/2. We're going to go down 1 over 2 over and over, down 1 over 2. And you can see how these things kind of hug close to that set right there. It's going to get closer and closer above it apparently. Down 1 over 2, down 1 over 2. Negative 1/2 x plus 1/2. Okay, and then up here, up 1 over 2, up 1 over 2. So getting these points right here, I'll draw a line through there. This is kind of a tougher drawing. And obviously more safe for a graphing calculator, right? But this right here is what it's going to approach, and I have kind of all my critical points I'm looking for. So let's go ahead and graph it from here. It's going to approach up, approach up from the top, curve down and approach down this way, okay? And then on this side, it's going to be looking like the opposite. As long as we have 1 point there, I think you realize that it is going to be on this side. Sorry about that. Terrible looking graph, but one more time. Ugh. Okay, I'll take it. There you go, 49. Last one, number 50. X minus 4 over negative 2x squared plus 32. Let's make sure there aren't any holes by factoring out the bottom. That would be factoring out a negative 2. We get x squared minus 16 left there. X squared minus 16 can factor out to x plus 4 times x minus 4. And there's a negative 2 still right here. So it looks like there's a common multiple of x minus 4 on top and bottom, which will cancel, which does mean there's a hole at x equals 4. A hole at x equals 4. Let's see if I can remember it this time. Yeah, so we'll see if we can remember that one. Okay. Now the rest of our graph then looks like f of x. Where are we? F of x equals 1 over negative 2 times x plus 4, just like that. Now, if I want to treat this like that a over x minus h plus k, I'm going to see if I can do it this way. Because if I can, I'd prefer to do so. So how do I make a? I can use negative 1 over 2. Negative 1 over 2 is negative 0.5. Let's pretend like on top was negative 0.5 and on bottom is x plus 4. And this is all plus 0. So how does this thing work as far as graphing it here? And remember, I have to keep in mind the hole. I have to make sure to put that one in. But first of all, your asymptotes will intersect at h value, which is negative 4, and k value, which is 0. So negative 4 for x, negative 4 for x. So it's over 1, 2, 3, 4, and 0 for y, which means they intersect here is where your asymptotes will be going through. These will be horizontal and vertical because of the, we're dividing by linear there. We don't have a higher degree on top, stuff like that. Okay, so we have that. Okay, now the next step is I guess the set of points after that, right? We have the asymptotes. Every time I remove myself 1 from here, I'm going to be doing this number divided by 1. So when I go over 1, I'll be going down negative 0.5 divided by 1. That's negative 0.5. Negative 0.5 over 2. Negative 0.5 divided by 2 is negative 0.25, negative a quarter. Here, I'll call this negative 1/2 to help out. Negative 1/2. So I can say not just divided by 2, but times 1/2. Negative 1/2 times 1/3 is negative 1/6, and negative 1/8, and blah, blah, blah. It keeps going over and over. Negative 1/2 on this side, this is, if I go 1/2 over, I'll be dividing by 1/2. Dividing by 1/2 is multiplying by 2. Negative 1/2 times 2 is negative 1. Over 1/3, negative 1/2 times 3 is 3.5. Negative 3.5. Negative 3/2, excuse me. And times 4 is negative, a quarter times 4 is, negative 2 right here. So it's it's smallish points right there. I'm sorry about that. Very smallish points just like that. I'll make sure of that hole. So going this way, at x equals 4, it's getting really, really close. At x equals 4, there's a hole right there and jumping through. And we can get some of the same points on the other side. For now, I'll just leave it be because we spent a lot of time on these graphs here. You can use graph and calculator table for most of these graphs anyway. So skipping some points of finding the horizontal and vertical asymptotes and intercepts, you can do if you know how to do kind of shortcut methods to these problems here. There's number 50. Okay, number 51. Let's sketch this graph, and then we'll do 52. 51, this is once again one of those y equals a times b to the x power, or x minus h plus k, as there is no hk shifts here. Our y-intercept, our asymptote is the x-axis right here, y equals 0. Okay, and we will be a units up from there when our exponent is 0. At x equals 0, we will be 4 units up. Nice. 1/2 is how much we multiply each value by and decrease our distance here to the asymptote. As x goes 1 over, will be 1/2 of our previous height. As we go 1 over again, half of our previous height, half of our previous height, half of our previous height, etc. As it tends towards 0. As x tends toward infinity, y tends towards 0. Dividing by 1/2 this way is multiplying by 2, right? Doubling height, doubling height, doubling height. There's an 8 right there. And there's a nice, pretty exponential function graph. Now I'm going to ruin it with a very ugly curve. Actually, it's not too bad. And I spoke too soon. There we go. Half arrow is my key, my favorite thing there, and full arrow that way. Domain, all real numbers. Range, y is greater than 0. Number 51. Number 52, once again, looks like we're not straying with our vertical asymptote here. It's not like there's a +1 out here or anything. So another horizontal asymptote at y equals 0. This time our a value is 1/2. That means we'll be 1/2 up from here when we do 5 to the 0 power. So x is 0, y is 1/2, boom, like this. Okay, every value after this, it looks like as we increase x by 1, we'll increase by a multiple of 5. So over 1 for x, we'll do 1/2 times 5. That's 2.5 right there. 2.5 times 5 is 12.5. So 10, 11, 12.5, maybe somewhere up there. So it shoots up pretty high there. 1/2 divided by 5 is 1/10. So over here, it's getting close to 0 at that point. So probably the only points I can really, truly fit there. And I'm going to just go and draw my curve from there. So it gets closer and closer to 0. Domain is still all real numbers. Range y is still greater than 0. I think all the questions here on out are only having to do with exponential equations or functions and logarithms. So I think everything here, you know, like I said, we're just working on those things. Let's see. Yeah, I think, you know, we're hitting the log stuff now. We'll get to 2 more log graphs, and then I think after that, just a lot of log stuff. Excuse me. Number 53, let's find the domain and range and then sketch the graph. Now, sketching the graph, like I said, is good to find that domain and range. X minus 1 has to be greater than 0. Cannot be 0 or negative here. We have to be a positive number. X is greater than 1 is your domain. Range for all these things, guys, is all real numbers. So I'm going to leave it at that. Range is all reals, all reals, all reals. But domain X is greater than 1 here. Now let's sketch the graph by using, when we're 1 more away from there, when x is 2, 2 minus 1 is 1, log of 1 is 0, plus 3 is 3. 1 over 3 up is the starting point. Now we use this 2 here. This 2 is how far we will distance ourselves from this asymptote when we increase y by 1. Y goes up 1, double your distance away. Y goes up by 1, double your distance away. Y goes up by 1, double your distance away. 4, 5, 6, 7, 8 right there. Y decreases by 1, we're halving our distance away. 1/4, an eighth, etc. So your graph is looking a bit like that there. Whoops. Anywho, something like that. Apparently I crossed my domain, but you know how it is. There's number 53. Nice looking graph. Number 54, starting with the domain here, x plus 2 has to result in a positive value. So x must be greater than -2. And within my domain, I'm going to have to pick numbers that are greater right there. And then I go to 1 away from x at -1. -1 plus 2 is 1. Log of 1 is 0. Minus 1 is -1. So 1 away, I'm at -1. That's my starting point. Now I'm going to use 3. Every time I increase y by 1, I will distance myself from there by a multiple of 3. 1 times 3 is 3. 3 times 3 is 9. 5, 6, 7, 8, 9. And we keep distancing ourselves in that direction. 27 would be next. Can't fit it. Decrease y by 1. I'm going to be 1/3 away from my asymptote. And then again, 1/9 away from the asymptote, etc. You're looking at a graph that's tending toward -2 for x as y goes to -infinity. And x and y go toward positive infinity. Ooh, that was pretty nice. X and y go toward positive infinity both the other way, even though it starts to flatten out more and more. It will never be completely flat, so your range again is all real numbers for these problems. Domain x is greater than -2. range, all real numbers. Okay, now a bunch of different log kinds of problems here. So this is where we're going to be making use of our our properties. I'll make use of parentheses a whole lot. And yeah, let's just go from there. Start solving for x and such. Okay, I won't have the properties put up, so I'll just exercise them as I say them. The difference of two log values can be written and condensed as one log value if you do division for both of them, like so. This will help me solve for x a little bit. Starting with, I can reduce 3 over negative 3 to 1 over negative 1. So I can put the negative 1 on top even, negative 1 over x, right? The whole point will be to solve for x. This is just as good. I can raise both these as exponents with 4 as a base here. So I can do 4 to this is 4 squared. 4 squared is 16. 4 to this is just negative 1 over x. So that's pretty nice. I can just make this negative 1 over x on this side. That cancels that out, right? 4 squared is 16. Multiply both sides by x. Divide both sides by 16. Cancel, 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 cancel. You're left with x equals negative 1/16. X equals negative 1/16. That is your final answer. This does fit within this domain as well. Even if I plug in an x in here, my result's not negative. If I plug in x into here, my result's not negative. So I'm set. I'm in the clear. Number 56, log base 7 of 9 plus log base 7 of x plus 9 equals 2. Same idea as last time, only this time it's addition. When you're adding two logarithms together of the same base, that's equivalent to taking the product of those two values within one log, just like that. Okay, now I could look to, I could look to distributing this stuff. In fact, I will this time, because otherwise I have to work with the fraction common denominator. Yeah, you'll see. I'll actually distribute what's inside here, even if it doesn't look best, because I don't want to do 2 divided by 9, even though later I'll have to divide by 9. Should be 9x plus 81 equals 2. Okay, 7 is now your base for both of these things. 7 to this is just 9x plus 81. This is just the conversion of logs. 7 to the second power is this. 7 squared is 49. And we're here. So subtract 81, divide by 9. That's all that's left. 49 minus 81 would be negative 32. And divide by 9x is negative 32 over 9. All right, so there's that. And just to double check that this answer works here again, negative 32 over 9 plus 9 is a positive number. So at least it's, it's not an issue. Not negative, not 0. Okay, same stuff right here that we just saw, log base 9 of. We have 5 and then subtraction. So this is 5 over x minus 7 here equals log base 9 of 13. Now both of these are log of the same base here. Technically I could do 9 raised to this power, 9 raised to that power, which will cancel them out. Yeah, two things of the same base mean we could just write 5 over x minus 7 equals 13. Those things cancel out. You're left with that. Multiply both sides by x minus 7. Divide both sides by 13. We'll get 5 over 13 equals x minus 7. And then see now I ran into the issue I didn't want to run into before. I'm going to add 7 over 7 plus 5/13. Now I have to deal with common denominator, this and that. So let's multiply top and bottom by 13. Next time I won't do that. 7 times 13 is 91. So 91 plus 5 all over 13 leaves you with 96 over 13. And I don't think that reduces at all. So x is 96 over 13. We're good. 96 over 13 is more than 7, right? It's 5/13 more than 7, so you're good there. All's good. Number 58, log base 4 of, log base 4 of. So as they're both the same base and they're being added, let's multiply, make it as one log. Log base 4 of 8 times negative 2x equals 2. Log base 4 of negative 16x equals 2. 4 raised to this power, 4 raised to this power. We'll get negative 16x equals 16. So x is negative 1 divided by negative 16. X is negative 1. Double checking, negative 2 times negative 1 is a positive number. It should work out there as well. No calculator needed. Evaluate each expression. This is basically asking us 5 to what power gives us 125. Another way of putting it is we don't know what our answer is, so we call it an unknown. So let's set it equal to our unknown x. Normally, this kind of helps a little more with that conversion process because you do what we did last time, 5 to both sides. This canceled, so you're left with 125. You're saying 125 equals 5 to the x. Obviously, this is the way of solving that x value, but this helps ask your question the right way. 5 to what power is 125? Now, that answer is 3. So 3 is the number we're looking for. Is it really x equals? No, but because I set it equal to x, you could. The answer, log base 5 of 125 is 3. Now, if you want to double check in your calculator, you can do log of 125 divided by log of 5. That will give you 3. That's how you can check these out. Same with number 60, which is what I'll do next. So 60 log base 6 of 1 over 216, like this, same thing, equals x. 6 raised to both powers here. 6 to the x power is 1 over 216. Okay, still might not know the answer off the top of your head there. I'll let you know that this answer is an integer. It is, so you don't have to use like the calculator. What you also could do here for these problems is, find a way to rewrite this as 6 to some power. So I happen to know myself that 6 cubed is 216, so this could be rewritten as 1 over 6 cubed. Well, 1 over 6 cubed is also 6 to the negative third power. So 6 to the x and 6 to the, negative third power are the same thing. 6 to x, 6 to this, x must be negative 3. So your answer here is negative 3. That's what this gives you. So you can try in your calculator log of 1 over 216 divided by log of 6, you'll get negative 3. Okay? Negative 3. Condense each expression into a single logarithm. Okay, so we just kind of did that in the previous equations where pluses mean multiplication. But before you do that, treat each log individually and see if there's anything else you have to simplify. Nothing in these two, but in this one, we have to take this 2 times the log base 3 of w is also log base 3 of w squared. And having the square inside the log is really what we're doing there. Here's log base 3 of v. Here's log base 3 of u. So now that they're separated by pluses, they're all logs of the same base. Now we can write it as a single logarithm, all with that base, and all as a product. U times v times w squared. The w is squared, nothing else is squared. That's the single logarithm right there, log of UVW squared. For some reason, the answer here says VUW squared. It doesn't know anything about alphabets or the order it was originally written. I have no idea why it's written that way. Okay, this single logarithm thing as well, just keep in mind right here, let's get that 5 up into the exponent. We'll have log base 2 of z squared, or excuse me, z to the 5th power, plus this 2 right here is a 1/2. So this can be rewritten as 1/2 times log base 2 of x, okay? So this 1/2 is going to go up into the exponent, so this will be log base 2 of x to the 1/2 power. Now, it's absolutely likely that, and I'm looking at the answer key, it's true, it's absolutely likely that when we condense this into a single logarithm, they're going to use x to the 1/2 power like fractional powers are roots. To the 1/2 power also means square root of. So we can do z to the 5th. This can be times the square root of x. So that's the ultimate way to condense this thing. And would x to the 1/2 power work as an answer? Yes. But if you're given a square root in a problem, it's important that you know that this also goes to the 1/2 power. So if you need to expand, you know how to take the 1/2 out, or to convert this into 1/2 to take it out. I'm sorry, 62 is supposed to be next here. 62, blah, blah, blah. 63, log base 9 of x squared times y, quantity to the 4th power, we are to expand this. Okay, what I want you to understand, because it's a bit ambiguous, is that the 4th power is actually inside the logarithm. So I will have this extra set of brackets here to state that that 4 is inside, which then allows you to pull it out in front here. I just know it's like that kind of problem because I know they wouldn't be too cruel as to give you another kind. So this 4 here goes outside first. This is 4 times the log base 9 of x squared times y. So now we get to separate this product into a sum of two different logs. Understand that this 4 is multiplying by both of these things. Log base 9 of x squared plus log base 9 of y. Okay, 4 is multiplying by both of them. So I can distribute the 4, and I will. So I'm going to distribute the 4, but on the same step, this 2 is going to be brought out in front. Let me do that right now. 2 is going to be brought out in front of just this log. So this will be 4 times 2, which is 8. So this will be 8 times log base 9 of x plus 4, distribute, times the log base 9 of y. There's your final set, fully expanded. That's kind of how we got those into that, to that setup there. Okay. Number 64, next. Log base 9 of these three, separate them to three different things, expand fully. And by expansion, they also do mean those exponents do come out, just like number 63. So let's split it up immediately to start off with. As it is a product, they'll be separated by plus with logs of the same base, all of 9. They apparently like these 9s for log here. V plus, this will be log base 9 of w to the 5th. Now, the only thing that's going to change from what's here to what the final answer is w to the 5th. This 5 will go out and multiply right here. So it should look like this as a final answer there. Boom. There's the expansion of those three. Fully, kind of one step. There's 1.5 steps right there. Just didn't want to rewrite everything else. And there's your answer to number 64. Okay, 65, we have log base 8. This is z squared times the cube root of x. I know that looks kind of strange where it's kind of iffy to see. So I'll write 2 steps this time here. I'm going to split these up first. Log base 8 of z squared. Also, on this step here, I'm going to convert the cube root of x into a fractional power. This is x to the 1/3 power right there. And again, that's just important to know because now I can take the 1/3 out and multiply it in front. So you might see the answer one of two ways. The 2 is going to come out as well. Either it'll say 1/3 times, like this, 1/3 times log of 8, or log base 8 of x. Or the 1/3 can be written as divided by 3, which when looking at the answer key is the way it's written. So it's written like this here, divided by 3. So again, do you have to write it like this? No. But knowing that divided by 3 is also 1/3 helps you in other problems, just like we had to do earlier. So this would be your final answer in this case. Lastly, number 66, kind of the same thing as number 63. In fact, they're very, very similar. This whole thing is square. This whole thing, the square is inside the log. So when I split this thing up, understand that the 2 comes out first. So let's do that. Let's get the 2 in front. This will be times log base 7 of x to the 4th times y. So this becomes, the 2's multiplying with everything. So it's multiplying with log base 7 of x to the 4th plus, again, all these were multiplication. For some reason, no division was used. Maybe division's next. Plus log base 7 of y. So the 2 is going to distribute in. This 4 will also come out in front. See, I like to do 2 steps at a time if I can. 2 times 4 is 8. So look, this is looking a lot like that previous problem. 8 times log base 7 of x plus 2, it's going to distribute 2 times log base 7 of y. So quite a bit like that previous problem we did, the number 63. There's your answer. 7 looks kind of wonky. Rewrite each equation in exponential form. Okay, so we kind of already talked about, what's happening here. Literally, this is your base. The result is an exponent there, so you could just straight up write it 216 to the 1/3 power equals 6. And that's kind of all you'd have to do. They're just asking you to write it that way. What I was saying before is how these things cancel. That's an important thing to know. If I raise it to these powers with this canceled, leaves you with 6, 216 to the 1/3. Another way of stating this is cube root of 216 equals 6, which this is a true statement, by the way. I don't think they'd give you that if it wasn't true. So either or here works. Looks like they give you this one on top as the answer on the key. And this one, same thing. This is base is 14, exponent is 2, result is 196. This is 14 squared equals 196. And that's it. They're not asking you to prove it's true. They're just asking you to rewrite it. And that's it. Not solving for anything. Oh, sorry, that's 68. Keep missing that. Number 69, solve each equation. 2 to the negative 2a power equals 1/2. Okay. A lot of different ways you can go about these problems here. We could start straight up with log. Let me show you, let me exercise another exponential property that I don't know I'll be able to do later. This is 2 to the negative 2 times a, like that, right? Well, it is absolutely true that you are allowed to do 2 to the negative second power here, raise that to the a power like that, and then you'll be left with this here. This will give you 1 over 2 squared to the a power is 1/2, which is 1 over 4 to the a power is 1/2. Now, you could continue this side as well. You could continue this side as well if you really, really want to attack same base, which is something I might consider doing. So I will do this 2 different ways from here. One way, I'll attack same base. Another way, I'll just do log. Okay. It's probably wiser that I would have done log another way to start off this problem, though. What I want to do is rewrite. Let's see. I could do it here. I could do it on this side. I'm going to rewrite the left side so that it has a base that matches 1/4. 1/4 to the a. If I make this thing 1/4 here, what power is this raised to? Well, the square root of 1/4 gives you 1/2. So if I put this up to the 1/2 power, this would be an equivalent. 1/4 to a equals 1/4 to the 1/2, then a is 1/2. That would be your final answer. This is just but one of many ways to do it. Second way I'll do it, just because I'm already in this form, is by logarithms. Logarithms is what gets you your power, your variable, down from the exponent. If I log both sides here, 1/4 like that, and this side, log this side, then I'm left with the a is going to come down. This will be a times log of 1/4 equals log of 1/2. And then a is going to equal log of 1/2 divided by log of 1/4. Log of 0.5 divided by log of 0.25. Other ways you can write this thing, just to kind of exercise and flex the property. Again, I know I kind of abundantly go over time a little bit when I do this kind of stuff. This is log of 1 minus log of 2 over, this is log of 1 minus log of 4. Log of 1 is 0, so these go away, and a negative divided by negative is a positive. So this result can also be written as log of 2 divided by log of 4. So there are a lot of different ways you can write this thing and get your answer. This thing will give you, if you use the calculator, this thing will give you 1/2 as your answer. I found a way of doing it without the calculator up here. That's something I wanted to work out. You could have used log from the very beginning as well. Don't get me wrong. You could have done the exact same thing as before, and your negative 2a could have come down in front. Would have gotten that kind of answer. A lot of different ways to go about that. Okay, so this one I'll do straight up with logs to begin with. Oh, I didn't know. You know, I take that back. I don't want to, right? If I want to do this without a calculator, because it's not saying with or without, but if I can do without, I'll try. So right here, what if I rewrite 25 with the same base as this left side? This side has 5 as a base. This one, probably easier problem than last time. Let me start this over. 5 to the 3x minus 1 equals 5 squared. So now I have 2 of the same base raised to different powers. Doesn't matter if they're the same or not. Same base means we can set the exponents equal to each other. 3x minus 1 equals 2. We're able to now add 1 and divide by 3. We'll get x equals 1. And it looks like that works out. 3 times 1 is 3, minus 1 is 2, 5 squared is 25. That's number 70. Okay, solve each equation, round your answers to the nearest 10,000th. This is where the calculator is now going to be used. We can do one part at a time here. Let's get the exact answer first, then enter that in the calculator. We'll be good to go. We got to solve for n. we have a product with this base. Let's start by dividing by 8. Let's get some stuff by itself, working toward isolating n. 6 to the 7.6 times n power equals 10. Okay, here's where logarithms come in. We're going to log both sides. And understand that this is going to go down in front of the log in just a moment here. So we'll do 7.6n times log of 6 equals log of 10. And now we have some division to do. Understand that both 7.6 and log of 6 are multiplying by n. So let's just divide both sides by 7.6 times log of 6. Divide both sides there, and we'll get an exact answer here. Excuse me, log of 6. We'll get the exact answer here, but let me approximate that now. N exactly equals log of 10 divided by 7.6 times log of 6. Go into the calculator here. We can use log. Whoops, none there. That was an old problem. Log of 10 divided by, use parentheses here because this is all in the denominator. You have a product in there. Do not want to upset your order of operations. And we're going to get a result of about 0.16909. What do we have to round to? 10,000th? So we'll do 0.1. N is about 0.1691. And the key agrees. There's number 71. Okay, 72, and I might as well leave this thing open just in case we have to use it. 72, same idea. We have b up in the exponent. We're going to divide by -9 to start. Notice that these two will not merge together. Order of operations have to do that first. So divide by -9. We're already left with a fraction that we can't reduce. So let's go ahead and see what to do from there. 3 to the -7b equals positive 77 over 9 because negative divided by negative. Now I can log both sides right now. And that'll bring our exponent down. That'll be -7b times log of 3 equals log of 77 over 9. I could also write this as log of 77 minus log of 9. Just giving you options here, whatever it is that's cleanest for you. I would argue this is probably worse to calculate, but hey, why not? Now I'm going to divide again to solve for b. I have -7 to divide by, and I have log of 3 to divide by. Those are both products. Multiplying by b here. Cancel on this side. They exist on this side over here. There's one way of writing it, the exact answer here. Let's get the approximated one now for number 72, doing the same thing as before. If I leave it in the numerator like this instead of like this, I really have to use parentheses now. Log of 77 divided by, minus log of 9, all divided by, close parentheses, all divided by, in parentheses again, -7 times log of 3. So your final result there, -0.2791. -0.2, that's a 0, 791. And that agrees with the answer key there as well. So that's rounded to the nearest tenth there. Let's say that that answer is correct. There we go. Simplify. Your answer should contain only positive exponents. Okay, this thing here, what we're going to do is just work with our exponential properties a little bit more. We have a product here. What I might recommend is that you reorder everything so that numbers are next to each other. Multiplication is commutative. We can reorder these things and still make this make sense. Like the m's can go together, and this n can be forever alone. Let's just leave that as is. Now, there are negative exponents to deal with. I'll get to those in a moment. 4 times 3 is 12. Same base, different exponents, whatever it will, add the exponents. M to the 3 plus -4, that's -1. Here's an n to the -1. So this would be our answer, but they say positive exponents only. Well, m to the -1 is 1 over m to the first power, so that goes in the denominator. N to the -1 is n over 1 to the first power, that goes in the denominator. Both of those go together, multiplied in the denominator, and you're left with 12 over mn. And again, for some strange reason, the answer key not only goes away from what was written first in the first time, but it goes away from alphabetical order. They have 12 over nm. No idea why. I'm going to leave my answer as is. Number 74, same kind of idea here. Now we have y's and x's with 4 and 3 again. I'm going to group the 4 and 3 together. Let me get rid of the calculator. The cursor's blinking. It's winking at me. 4 times 3 is there. Let me get my x's next for alphabetical purposes. X to the negative first power times x squared times, this is y to the first power there, that y, and this is y to the negative fourth. Okay, I've accounted for every number there. 4 times 3 is 12. This is going to be negative 1 plus 2. That's 1. X to the positive first power. This is 1 plus negative 4, which is negative 3. So y to the negative third power is going to be y to the positive third power in the denominator. 12x over y cubed is the simplified form of that answer. 75, we're going to solve this equation in 76 as well. Round our answers to the nearest 10,000th. Our calculator will be handy again. Let's get p by itself, same way we did last time. Only this time we have 10 added to this, not multiplied. So let's subtract 10 to start. P plus 9, that's going to equal 86. Let's 86 this guy. Let's log both sides. Log this side. Looks like a P and a Q. That's why I'm trying to write the 9s a little higher. Equals log of 86. Now, by the way, when I'm saying log here, I'm not mentioning the base. In your calculator, base is 10. When you get your answer, base will be irrelevant. Okay, P plus 9 is going to come down. Note that I'm using it as a quantity to make sure you know both of these are being multiplied by log, not just the 9. So this is log of 11 left in here, log of 86 over here. Okay, so I got 2 more steps to do. I'm going to divide both sides by log of 11. As you can see, it'll cancel out on the left side. I'll be left with P plus 9. And on the right side, I'll have log of 86 over log of 11. Now I subtract 9, and 9 is going to subtract from the entire thing, not just exist in the numerator. This will be P equals log of 86 over log of 11 minus 9. This is what I'm going to calculate. By the way, you can also write this, not that it helps you with the calculation, but this is log base 11 of 86 minus 9. This and this are the same thing. I'm letting you know in case you're asked to calculate something like this here in the future. So let's approximate. I'm going to be using this, though. P is approximately equal to. Let's go ahead and take a look at that. Let's do log 86. Where's log? 86 divided by, close parentheses, log of 9. Excuse me, log of 11 minus 9 will be to the nearest 10,000th, negative 7.1424. We're going to round up. So negative 7.1424. It's your approximate answer for P. Number 76, same idea as last time. I'll leave the calculator open because we're going to have to use that. Add 7 to both sides. 29. Log both sides. Okay. Negative 7x comes down, and again, both of them are multiplying by this whole set, log of 8, equals log of 29. Okay, this does act a little bit more like the previous problems we had. I'm going to divide by the negative 7 and the log of 8 altogether. So x will only be left here, log of 29 here, and again, this is negative 7 times log of 8. That's in the denominator. There's exact answer. Okay, approximated answer to the nearest 10,000th. Once again, go into the calculator. We'll do this divided by, again, parentheses in the denominator because we have a product inside there. Negative 7 times log of 8. And then that gives us about negative 0.2313. Answer key agrees. We're good there. Got 4 more problems to go. Solve each equation. Okay, solving for x here, they all have the same base. What I'm going to do is try and get this base here by itself to begin with, so I'm not dealing with a fraction on this side with x. I'm going to add this log base 5 of 3 over to begin with. So I have log base 5 of x minus 6 equals log base 5 of 47 plus log base 5 of 3. These can be written as a product together. Log base 5 of x minus 6 equals log base 5. I'm going to do 47 times 3. That number is 141. Now I have two logs of the same base here, and all I'm trying to find is the number inside. I can just set these two equal to each other. X minus 6 is 141, so x must equal 147. And that's your answer to number 77. Number 78, let me get rid of the calculator. Number 78, also same basis here. We're going to solve for x. Let's just do the same thing as we did last time. I'm going to join these together, subtract log base 7 of 8 over to this side. Looks like I'm going to be dealing with a fraction, unfortunately, here, but log base 7, let's see, I'm left with negative log base 7 of x plus 9 over here. And here I have log base 7 of 19 minus log base 7 of 8. Okay, that's a division there. Subtraction of logs is division of. So negative log base 7 of x plus 9 equals log base 7 of 19 over 8 right there. Okay, now this part here isn't as easy as it looks. This is a negative 1 outside of here, but we can't just say it's going to be negative 1 times this inside equals this inside. No, see, this is a part of our log that we're going to have to condense a little bit. As a negative 1 goes in here, let's go ahead and bring it up into the exponent right there. Okay, now it says log base 7 of x plus 9 to the negative first power equals log base 7 of 19 over 8. So you can see the number ain't as easy as it was going to be. It wasn't just negative 1 times x plus 9. This is 1 over x plus 9. So both logs are the same. Now we can just write this as one set without logs. 1 over x plus 9 equals 19 over 8. Okay, well now the fractions kind of help themselves out because we get to cross multiply here. 8 times 1 is 8. This is 19 times the quantity x plus 9. You can see I'm going to be, I'll go ahead and distribute. We'll get 19x plus, that would be 171. Subtract 171. We'll get 19x equals negative 163. And divide, we'll get x equals negative 163 over 19. Tricky problem with that log stuff because it almost sounded like the other answers prior to that. Two more. Natural log of negative 3x plus natural log of 4 equals 1. As it is same log of same base, it's log base e. We can combine these both as a product. Negative 3x times 4 is negative 12x. This equals 1. Remember, this is log base e, so to cancel this out, we'll use base of e to these powers here. E to this cancels. Negative 12x equals e to the first power. So divide by negative 12, you get x equals negative e over 12. It's fine to leave the answer like that. Assume no calculator in a problem like that. That's all you get. That's your answer. Last problem here, number 80. We'll do natural log of, here's a product, 4 times 5x squared. That's 20x squared equals natural log of 20. As they have the same log with the same base here, we can just write 20x squared equals 20. Continue to solve. Divide by 20. X squared is 1. So x is plus or minus 1 here. So that would result in your final set of answers there. Double check and make sure nothing's extraneous. 1 squared is positive. Negative 1 squared is positive. Looks like there won't be any issues there. You'll get the same answer. That's it. Fiend!